Hello, welcome to another video for Lambda class. We're discussing mathematics here, and in this episode we're going to review the Euclidean division algorithm. This is something that we have been using quite a bit now, so I think it's time to show a proof of that theorem. It's an extension of what we have done already in high school and middle school, but for polynomials over a field. First of all, we need to talk about the degree of a polynomial, how it behaves when we multiply and add two polynomials together. We're then going to discuss the proof of the Euclidean algorithm, and then we're going to show that for polynomials over a field, then the number of roots that that polynomial has over that field is bounded above by the degree of the polynomial, thing which is not true when we talk about polynomials over just a ring. Okay? Well, so let's start. We already know most of these things, so we're going to go over them kind of quickly. Let K be a field, and consider the ring of polynomials over that field. The ring of polynomials over K. This is the set of all the expressions of the form P of X that are sums of coefficients in K times X to the ith power, such that all the AI belong to K and N is a natural number or 0. Okay. First observation, big X is not an element of K. It is just a token. It's just a symbol that we use in this notation. It's only a symbol. It interacts with itself in this fashion. Every time we multiply x to the ith power times x to the j power, we get x to the I plus j power. Okay, so we know how to add polynomials and how to multiply them. This enables us to add and multiply polynomials via the distributive law. Okay. We're trying to formalize what we already know how to do, so we just need to say that. Well, there's this notion called the degree of a polynomial, okay, which we can think of it as a function that takes a polynomial and gives us a number which is natural or 0 that is going to be defined in this way. So defined by if f of big X can be written as this, meaning that we got a sub 0 plus a sub 1 times x, then a sub n times big X to the nth power, then the degree of f is simply n, okay? That's the degree of the polynomial. If the polynomial consists only of 0 coefficients, then we will define the degree of f as minus infinity. Okay? So this allows the following observation. First, the degree of the sum or subtraction of two polynomials is bounded above by the maximum of the degrees. Because when we add two polynomials together, maybe the powers of a higher degree cancel out. So in the end, we get a polynomial of a smaller degree. And second, which is very important, the degree of the product is the sum of the degrees. So when we have two non-zero polynomials, the degree that we get is the sum of the degrees. If f, g have both non-zero degree or positive degree, then the degree of f times j is strictly greater than the degree of f and strictly greater than the degree of g. And this is very important. We're going to use this today. Yeah. So once we have talked about the degree, it's time now to state the Euclidean theorem. So that's Euclidean Division theorem. Okay, so let's state the theorem and then we'll prove it and we'll be happy with that. So let f and g, two polynomials over a field K with a degree of f being n, the degree of g being m. Then there exist unique polynomials q and r, also in K of x, such that f can be written as q times g plus r, with the important distinction that the degree of r has to be strictly less than the degree of g. This is a crucial condition for this theorem to work. Okay, this also allows r to be 0. Okay, this also allows r to be 0. So this is an existence theorem. It says, okay, under these conditions, these two polynomials exist. But not only that, it also says that they're unique. That I cannot find two pairs of polynomials, q, r, q prime, r prime, so that they can be combined in this way and produce f. So this is an existence and uniqueness theorem. So let's prove uniqueness now. let's try uniqueness. Suppose there exists Q1, R1, Q2, R2 such that F can be written as Q1 times G plus R1 or Q2 plus G times G plus R2. So what happens when we subtract? We get F minus F, that being the zero polynomial, and then we have Q1 minus Q2 times G plus R2 minus R1, right? So if we rearrange this equation, what we get is the following. We get Q1 minus Q2 times G being R1 minus R2. So if there exists two pairs of polynomials that combined produce F in this way, then what we get is this equality. But this has a problem, right? So what do we know from this is that this product has degree greater to or equal to the degree of G. So this has at least the degree of G. And at the same time, this side of the equation has a degree strictly less than the degree of G. Okay? So there cannot be different pairs. The only way in this that this equality can be held is that both sides are minus infinity. Okay, so what we need to say now is that the only way of this equation can subsist is that Q1 is actually Q2 and R1 is actually R2. This is the only way this equality can hold because of the degrees, right? So we're going to have distinct pairs Q1, R1, Q2, R2 such that F can be written in this fashion. So there we have uniqueness. Okay, if we can write it in this way, it's a unique way of writing that polynomial F. So with uniqueness out of the way, we need to establish the existence of Q and R. So let's try cases. See, let's take the case of M being greater than N. In that scenario, we can take Q equal to the zero polynomial and R equal to F. So F is trivially written as this. Okay, so we're left with the case M being at most N. Okay, and what we're gonna do, we're going to proceed by induction on n. Okay, so we're gonna do an inductive proof. So let's see the base case n equal to 0. So what we have now is that m has to be 0 as well. So in this case, both f and g are constants. So what we have now is that f of x has to be the constant a sub naught, g of x has to be the constant b naught, and now this is easy, right? Since b sub 0 is not 0, because the degree of g is not minus infinity, right? Then taking q as a sub 0 over b sub 0 and r equal to 0, then we have f can be written as this. Okay, so this happens when n equals to 0, right? And this is the place where we use that case a field. Here is where we make use of k being a field. We can invert b naught, right? So we can form that fraction. So the base case is actually very, very easy. So let's go to the inductive step. Inductive step. The theorem holds for all polynomials of degree at most n. So this is what we call the inductive hypothesis. Inductive hypothesis. Okay, and with this inductive hypothesis, we're going to show that the theorem holds for polynomials of degree n plus 1. If we show this, we're gonna be proving the complete theorem. So assuming that it is valid for every polynomials of degree at most n, we're going to show that it's still valid for polynomials of degree n plus 1, right? So let's go ahead. Suppose now that the degree of f is n plus 1, all right, and the degree of g is at most n plus 1, right? So we can think of f of x as a sub n plus 1 times x to the n plus 1 power plus a polynomial of degree at most n. And the same for g, right? We can think of g as being written as b sub m to the times x to the n power plus g sub m, right? Where this fellow right here has degree at most n, right? And this fellow right here has degree at most n minus 1, right? So what's the idea? Idea is to try to cook a polynomial of degree at most n using f and g, and then apply the inductive hypothesis to that polynomial. So that's not very complicated, and we can do that. So let's take a look at f minus a sub n plus 1 over b sub m x to the n plus 1 minus m times g. Let's take a look at this polynomial right here. Especially what happens when we multiply this polynomial with g. Something will happen in the lower terms, but most importantly, we need to take a look at the monomial of highest degree. So when we multiply this power of x with this power of x, the minus m and the m cancel out, and we get x to the n plus 1 power. Then also what happens is that the b sub m in the denominator will simplify with the b sub m in the numerator, and what's left is a sub n plus 1 times x to the n plus 1 power. When we take the subtraction of f minus this product, what we get here is a polynomial of degree at most n plus 1. At most n. So the inductive hypothesis says that there exist polynomials Q on R such that f minus a sub n plus 1 over b sub m times x to the n plus 1 minus m times g can be written as q times g plus r, right? So what's left now is rearranging the terms. So we move this part to the other side, and what we get now is q plus a sub n plus 1 over b sub m times x to the n plus 1 minus m. All this multiplied by g plus r. So this is actually what we were looking for, because now this will be the quotient and this will be the remainder. So we were given a polynomial of degree n+1, which is called f, and a polynomial g. And using the inductive hypothesis, we were able to show that this polynomial f can be written in the fashion that we wanted. Okay, so theorem is true for all polynomials of degree n+1. Okay, the induction principle states that the theorem is true for polynomials of arbitrary degree. So we have proved the Euclidean Division theorem. We have done it using induction principle. Okay, so this will have several consequences, especially when we want to talk about roots of polynomials. And we're going to state that, and it's going to be very, very easy to understand. We have already mentioned this about linear factors and roots, so we're going to be very brief. The purpose of this video was to show a proof of this polynomial and see how it is structured. So as a corollary, let f be a polynomial in k of x, and let a belong to k. So x, the polynomial g x minus a divides f if and only if a is a root of f. That is, f at a is 0. So this Euclidean theorem establishes a relation between the factors of f, here g is a factor of f, and roots of f. All right, so one happens only if the other happens. Short proof. Let's prove that if x minus a divides f, then a is a root of f. Let's prove that if x minus a divides f, then f at a is 0. Okay, so the Euclidean theorem guarantees the existence of Q and R such that f can be written as x minus a times Q plus R. This can be done using or invoking the theorem. So the Euclidean theorem guarantees that Q and R actually exist. But now take a look. the degree of x minus a is actually 1 because it's a polynomial of degree 1. It's a linear polynomial. So that implies that the degree of r has to be strictly less than 1. So that means that the degree of r is less or equal to 0, right? But then the hypothesis that we're taking is that x minus a divides f. If x minus a divides f, that means that r is actually 0. So what we get is that f can be written as x minus a times q. This is why we called x minus a factor. It's a linear factor of f. And now it's easy, right? Now what happens when we evaluate? F at a. So that's easy. F at a has to be a minus a times q at a, and this is 0 times q at a, and this is 0. So we have shown that a is a root of f. And we have shown one of the implications in this corollary. Reversely, if a is a root, then we need to show that x minus a divides f. And that's simple. Conversely, suppose f at a is 0. Okay? We know that the Euclidean algorithm guarantees the existence of G and R such that f of x can be written as x minus a times q of x plus r of x. Right? Since the degree of x minus a is 1, then the degree of r has to be at most 0, right? And the hypothesis f at a equal to 0 then gives the following. If we take this line and replace x with an a, what you get is f at a, then a minus a times q at a plus r at a. So by hypothesis, this is 0. 0 times q at a plus r at a. So what we have now is that r of a is 0. And since r is a constant, then r of x is always 0. R is a constant polynomial, and we have shown that that constant polynomial is 0. So what happens in the end is that f could actually be written as x minus a times g of x. That means that x minus a divides f. That is, x minus a is a factor of f, linear factor of f. And this is the end of the corollary. So the Euclidean algorithm not only allows us to express f as a combination of quotients, remainders, and dividends, but also relates the behavior of a polynomial function and its linear factors. So there's a relation between the multiplicative structure of k of x and how polynomials behave as functions. That is terribly important for us, and we will exploit that in the following video. This is just opening the door to the idea of interpolation and how that will allow us to send messages in a very specific way. Okay, so I hope you enjoyed this video, and I will hope to see you in the next one. Okay, goodbye.